Hey guys, Ms. Marusik here, and in this video we're going to talk about balancing redox reactions using half reactions. We're going to write both an oxidation half reaction and a reduction half reaction, and what we're going to do is we're going to try and balance the two of those with each other. We're going to try and ensure that the same number of electrons is both lost and gained in the overall reaction. And as a result of doing that, what we'll end up doing is balancing the equation overall. Now, for this to work, it's important for us to remember our oil rig saying that oxidation is a loss of electrons, but that means oxidation numbers are increasing, they're becoming more positive, and a reduction is a gain of electrons, that our oxidation number here is going down or becoming more negative in that gaining of those negative particles. Now, I know there's a whole bunch of steps here. We're going to kind of talk about the steps together as we do these examples. So let's kind of go ahead and jump into the first one here. So what we're given is an overall equation that our goal is to write both the oxidation and reduction half reactions to ensure that the electrons lost and electrons gained are equal. And in that process, we're going to end up placing coefficients into each of these blanks. Now, for this to work, I first need to figure out what my oxidation numbers are to begin with. I need to see which ones have changed from side to side. So the very first thing I'm going to do is assign my oxidation numbers just like we did in the last video. So for HNO3, I would first assign hydrogen at +1. I would assign the oxygen at -2. However, there are 3 of those. So for all of this to cancel out to 0, the nitrogen here had to have been a +5. For the H2S, I would have assigned the hydrogen first at +1. However, there are 2 of those in this process, and so therefore the sulfur had to have been a -2 here to all cancel out to 0. For the nitrogen monoxide, I would have first assigned the oxygen at -2. So for all of this to cancel out to 0, the nitrogen here had to have been a +2. So then on H2O, I would have assigned the hydrogen at +1. There are 2 of those in that substance, so oxygen here to balance out had to have been a -2, which is what I would have assigned it anyway. And then last but not least over here I have sulfur, but it is an element by itself, and so therefore I'm going to assign it an oxidation number of 0. So now the next thing I would want to do is notate what has changed from side to side on those oxidation numbers. I notice here that I have a change in the nitrogen from a +5 down to a +2, and I also have a change in the sulfur from a -2 to a 0. So what I'm going to do is I'm going to start writing some half reactions for these. I'm going to say, hey, nitrogen changed from being a +5 to a +2, and my sulfur changed from being a -2 to 0. All right, next thing I'm going to go ahead and do is identify which of these is the oxidation and which of these is the reduction. If I notice the nitrogen is going from a +5 down to a +2, that's becoming more negative, and so therefore I can assume that this is my reduction. For the S-2 going up to 0, that's becoming more positive, and so I can assume that that's my oxidation. Now, the reason why that's important to identify is because now I can think about where my electrons should go in these processes. For nitrogen, if it's a reduction, then that means I'm gaining electrons. So I should have electrons happening on this reactant side here. Now, if you're trying to think about how many electrons, you want to use enough that would cause that total change to occur in the oxidation number. If I'm changing my oxidation number by 3 from a +5 to a +2, that means I need to be gaining 3 electrons. By the way, math-wise, this should work out. If you think of the arrow as being like a big equal sign, 3 negatives and 5 positives should total a +2, and in fact it does. So now we would do the same things for sulfur. However, for sulfur, it's an oxidation, so that's a loss of electrons. So that means my electrons here are going to be on the product side. And so a -2 down to 0 would mean I have a change of 2, so therefore I'm going to have 2 electrons. Or I could say that 0 and 2 negatives would equal a -2. Again, you can see that the math works out. So here's the issue. Our number of electrons that we gained is not equal to the number of electrons that we lost. And so therefore, we're going to have to figure out what I need to do to make those equal. So this is where I need to think about the lowest common multiple between 3 and 2. Lowest common multiple between 3 and 2 is 6. I would want to ensure that I'm gaining 6 electrons and losing 6 electrons for those to be equal to each other. Well, for us to here be gaining 6 electrons, I'm going to need to multiply this half reaction by 2. For us to be losing 6 electrons here, I need to multiply this half reaction by 3. And what I'm going to do now is I'm going to translate that information into some coefficients up above. So again, we know that we're gaining 6 and losing 6 electrons. So those are going to cancel out. So let's see here for the nitrogen plus 5, I need 2 of those. Well, right now in this equation, I only have 1 of those nitrogen positive 5s. And so therefore, I'm going to put a 2 in front of that substance. I also need 2 of the nitrogen positive 2s to ensure that, again, I'm gaining 6 electrons. If I look right now, I notice I only have 1 nitrogen positive 2. And so therefore, I'm going to put a 2 as a coefficient in front of that substance as well. I'm going to do the same thing now for the sulfurs. I need 3 sulfur negative 2s to ensure that I'm losing 6 electrons. Well, right now in my compound up here, I only have 1. And so therefore, I need to put a 3 in front of here. And I also need 3 of the sulfurs that are neutral on the product side. I notice right now that I only have 1, and so therefore I need to put a 3 here. Now that should balance almost everything. We do want to double check and make sure there's nothing else that needs to be balanced. If you notice, I didn't touch this water over here, so I probably want to make sure I address that. So let's kind of look at the hydrogens and oxygens, because those were elements that I didn't address down here. I noticed that on my reactant side, I have 2 hydrogens and another 6 hydrogens here, so that's a grand total of 8. And so to get 8 hydrogens over here, it would make sense to put a 4 in front of that compound. Now let's see if that worked for the oxygens as well. I notice I have 2 times 3, so I have 6 oxygens over here. I notice also I already have 2 oxygens here, so getting another 4 from the water would ensure that that all comes out to be perfect. So we might need to finish balancing with our normal kind of process at the end, just to double check and make sure that everything has been addressed in that process. Now the last thing I can do is identify the exact substance that got oxidized and reduced. When I'm identifying these, I always want to talk about what they looked like on the reactant side. So you could either say that the nitrogen plus 5, or that the compound itself, the HNO3, underwent the reduction. So we say that that substance got reduced. The sulfur negative 2, or the compound that it came from, the H2S, is what got oxidized. It underwent the oxidation there. All right, let's roll through some other ones. Now, I know some of you are looking at this and being like, hey, Marusik, I could have totally balanced this without doing this half reaction business. Like, why was that necessary? Well, I'll be honest with you. Yeah, could you have balanced this one kind of the old school way? Sure, but I'm going to warn you, that is not always possible. Let's look at one where that would not have been possible. All right, so our one at the top of the next page. Aluminum plus Pb plus 2 yields Al plus 3 and Pb. Well, that looks kind of balanced already, right? I got one aluminum, one lead. You're like, isn't that balanced? Nope, it's not balanced. Not when you're talking about electrons. And remember, that's what this process is trying to do. It's trying to ensure that electrons lost and electrons gained are equal. So we have to be really careful on those net ionic equations, because even though it might look like it's balanced, it might not actually be balanced. So I'm going to start this off just like I did the previous one by assigning my oxidation numbers first. Aluminum here's by itself, so that's 0. Now this Pb has a positive 2 charge with it, so that means its oxidation number is that positive 2. And if you want to rewrite it, you can, or you could just leave it as is. Same thing goes for this aluminum here. That's a positive 3. However, this lead here doesn't have anything shown with it, and so we assume that it's neutral. And so the next thing I would do is identify what changed from side to side. I see the aluminum went from being 0 to aluminum +3. Well, that became more positive. That oxidation number increased, and so therefore this must be my oxidation. The other thing that changed, of course, was the PB. PB went from being a +2 down to neutral PB. So that oxidation number decreased or went down on a number line. It became more negative. And so this was my reduction. All right, so next thing I would want to do is place my electrons. For the aluminum, if it's an oxidation, that's a loss of electrons. Those electrons need to go on your product side. And if I'm going from 0 to +3, well, that means I've got to change 3 electrons there. For PB, it was the reduction, and so therefore my electrons need to go on my reactant side. I need to gain them. I see that this oxidation number changed by 2. And so that means I would want to gain 2 electrons. All right, 3 and 2, those electrons lost and electrons gained do not equal each other, so I need to make them equal out. And just like we saw in the last example, the lowest common multiple between 3 and 2 is 6. Now, not always are you going to have to multiply one of these. Like, let's say this had 1 here, 1 electron, and this had 2, then I would have only needed to multiply the 1 half reaction. So these just happen to be that both of them that we've done so far, I needed to address both of my half reactions. So I'm going to do that by saying, hey, I needed this half reaction to happen twice. I need this half reaction to happen 3 times. And so now I'm going to go translate that information up above. I need 2 of the neutral aluminums. I need 2 of the aluminum +3s. I need 3 of the PB +2s. And I need 3 of the PBs that are neutral. And also, as we said earlier, that means 6 electrons would have been lost, 6 electrons would have been gained, and so those would have been canceled out as well. Last but not least, let's state what got oxidized and reduced. Remember, we always reference what it looks like on the reactant side. So we would say here that aluminum that was neutral was the substance that was oxidized. And we would say that the PB on the reactant side, which was a +2, was our substance that got reduced. All right, let's do one more together. So again here, what I'm first going to need to do is assign myself some oxidation numbers. So let's go through. On ClO3 -1, I would have assigned the oxygen first at -2. There are 3 of those. So to cancel out to be a -1, that means my chlorine here had to be a +5. A +5 and a -6 would have totaled to a -1. Water, we assigned that one earlier. So as a reminder, it's +1 and -2. And what happens is that there's 2 of those hydrogens, and so that's why it cancels each other out. Now, I2 here is a diatomic, but it is neutral because it's all by itself. It's an element by itself. This IO3 -1, I would have assigned the oxygen first at -2. However, there are 3 of those. And so what happens is, again, that iodine had to be a +5 over here. My Cl is -1, so that's -1. The hydrogen's +1, so that's going to be +1. All right, so now let's look and see what changed from side to side. I noticed that chlorine went from being a +5 down to a -1. So Cl +5 down to Cl -1. I notice that the iodine is 0 over here. Now, here's where we have to be really careful. On these half reactions, if something is a diatomic, that subscript gets carried down here. So I'm going to put I2 at 0. Now, this is where we have to be really careful on this half reaction. I had iodine becoming +5, but because this 2 was here, I need to make 2 of these on that half reaction. So diatomics are the one time that we carry down those subscripts into our half reactions. All right, so now I'm going to look to see who got oxidized and who got reduced. So I can see here that chlorine went from a +5 all the way down to a -1. And so that is definitely my reduction there. Whereas the iodine went from 0 up to +5, so that oxidation number increased. So that would definitely be my oxidation. Again, you can't have one happen without the other. So if you think you have two reductions, I would check again. All right, so the next thing I'm going to do is think about my number of electrons. Now, on this chlorine, going from +5 to -1, we know it's a reduction, so we know we're going to gain those electrons. But be very careful with the count here. I am not only going down by the 5 to get me to neutral, but then I'm also going down by an additional 1. And so what that means is that this is going to be a grand total of 6 electrons here. And if you look at your math, it should make sense. I have 6 negatives and 5 positives giving me a -1. Now the iodine, we got to be careful with that diatomic. There were 2 iodines that were each changing by a +5. So if I have 2 things changing by 5, then that means I'm going to have to put 10 electrons over here, which seems like a really big number, and it is, but that's how many we need to put. So again, diatomics, get that 2 brought down, and then I have to double that count of my electrons to address the 2 that are changing. All right, so here's the problem. 6 and 10 do not equal each other. Electrons lost and electrons gained are not equaling each other right now. I need to make those equal. And I think of the lowest common multiple between 6 and 10, and that would be 30. So to get 6 electrons to 30, I would multiply this by 5. To get 10 electrons to 30, I would multiply this by 3. So now let's translate this information into our equation up above. So to get those 30 electrons gained, I need 5 chlorine plus 5s. Well, right now I only have 1, and so therefore I need to put a 5 here. I also need 5 chlorine -1s. Right now I only have 1, and so therefore I'm going to put a 5 over here. So now, on the iodine, I need 3 diatomic iodines. Right now I have 1, so therefore if I put a 3 there, that'll work. Now we got to be careful on this one. I need 3 times 2. So I need 6 iodine plus 5s. Right now I only have 1 in there, and so therefore I'm going to need to put a 6 here to balance that. So be careful on that. Otherwise you don't end up with the same count of iodines on either side. All right, now that almost finished us balancing. By the way, you notice this one has water and H+1 included in here. And so that means that this is an acidic example because again, it has the H2O and the H+1. You don't really need to know that, but if you were taking this class in college and they told you it was acidic, they might not have included that H plus and H2O in the equation, and so you would have had to know that you needed to include that in order to balance it out. Here they go ahead and give it to us for AP, so that's really nice of them. But I do need to finish balancing here. So I'm going to actually look at my oxygens first. Because I noticed the hydrogen here doesn't have a coefficient, so that would be kind of hard to start with that. So I'm going to start with the oxygens. I notice I have 5 times 3, so that's 15 here, plus that 1. On this side, I have 6 times 3, so I have 18. So if this side has 18, and right now I only have 15 over here, then that means I'm going to need 3 more over here. So I'm going to put a 3 there on H2O. Now what that does is that gives me 6 hydrogens, and so therefore I would put a 6 over here, and that should finish balancing everybody. So you can see that one would have been really hard to balance using kind of a normal balancing process, yet we could do it fairly easily when using half reactions. Now the very last thing we want to talk about on here is how to identify a reaction as being a redox reaction versus our other types of reactions that we've already talked about, acid-base reactions and precipitation reactions. So to clarify one more time the difference between these. For an acid and a base reaction, what we're going to be looking for is losing and gaining an H+. We're going to be looking for those conjugate pairs. For redox reactions, we're going to be looking for changing oxidation numbers. Finally, for a precipitation, we're going to be looking for a solid formation. All right, so let's go through each of these. We have one of each type on here. You might be able to kind of predict what these are without me, but we're just going to go ahead and talk about them together. So to look here at this first one, I notice very clearly I have a solid forming here. And so it's a really good bet that this guy is our precipitation, and it is. However, to rule out the other two, I notice that I don't even have hydrogens involved here. So this is definitely not an acid-base thing, okay? And if I look at my oxidation numbers, I have +2, -1. And in this compound, I would have -1 times 2, and the calcium would be +2. And so those have the same oxidation numbers. So no oxidation numbers changed in that process. So precipitation was a really good bet. All right, let's look at this next one. Woo, that looks like a doozy, doesn't it? And if I start looking at it, I'm like, well, I don't see any kind of solid forming, so that rules out precipitation. And I don't see any kind of transfer of losing and gaining an H+. Like, yeah, I have H2O over here and OH over here, but it wasn't like I transferred a hydrogen from one substance to another. So let's check and see if oxidation numbers changed. Well, I can kind of tell off the bat that they did. I noticed that bromine here is by itself, so that's 0. And I see bromine over here has a -1. So even if I don't know what else is happening in there, I know at least one oxidation number changed. Now, if one changed, there's got to be another that changed. And actually, I'll tell you what it is. Over here in the BrO3 -1, oxygen is -2 times 3. Well, this other bromine here ends up being +5. So you notice bromine changed from being 0 to -1. And it also changed to being a +5, where you have the same element, the same substance that's both oxidizing and reducing. We would say that that is a disproportionation. You don't have to know that for AP Chem, but it's kind of a side note that we can have the same substance doing both processes. And so therefore, this is definitely my redox reaction here. Last but not least down here, I see that I do not have a solid forming, and so therefore I can rule out precipitation. If I go assign oxidation numbers, hydrogen's +1, and there's 3 of it, so nitrogen would be -3. Chlorine's -1, hydrogen's +1. Here, the hydrogen would be +1, and to get to a +1 overall, if there's 4 of those, nitrogen must have been a -3. And here, the chlorine is a -1, and I can see nothing changed oxidation numbers from side to side. But look what I do see. This hydrogen here ended up transferring to the NH3 to become NH4 +1. So that HCl, in losing that H+, that was acting as an acid, meaning the NH3 was the base. Our NH4 +1 would have been our conjugate acid, and our Cl -1 would have been our conjugate base. So what we have here is one of those acid-base reactions. All right, hopefully we're feeling good about assigning oxidation numbers, writing half reactions, identifying who got oxidized and who got reduced, balancing an overall equation using that half reaction method. If you have any questions or need any help, please feel free to email me. Bye, guys.